Newton's laws of physics, formulated by Sir Isaac Newton in the 17th century, are a key in the understanding of classical mechanics. These three fundamental laws encapsulate the principles governing the motion of objects, offering a framework that has shaped our comprehension of the physical world. The primary objective of this experiment is to apply and validate Newton's laws of motion in the context of using a toy car. Specifically, the goals are Newton's first law, or the law of inertia, to observe and analyze how the toy car behaves when initially at rest and in motion, affirming the concept of inertia as described by Newton's first law. Newton's second law, or the law of acceleration, to investigate the relationship between the applied force, the mass of the toy car, and its resulting acceleration, verifying the principles outlined in Newton's second law. Newton's third law, action and reaction, to examine the interactions between the toy car and external surfaces, validating Newton's third law by identifying and analyzing equal and opposite reactions during motion. By conducting these experiments, the aim is to gain a practical understanding of how these fundamental laws influence the motion and behavior of the toy car, providing tangible insights into the application of Newtonian physics in a real-world scenario. Newton's first law, F equals ma, where F is force, m is mass, and a is acceleration. When the toy car is moving at a constant speed, the applied force is balanced by forces like friction and air resistance. For the experiment for the first law, which is constant speed, start time was 5.55 and the end time was 7.14, which makes the total time the car traveled about 1.19 seconds. The velocity, which is distance over time, was approximately 0.84 meters per second, and the acceleration, which is velocity over time, approximately 0.71 meters per second square. Newton's second law, F equals ma. By systematically varying the force applied and measuring the resulting acceleration, the experiment provides empirical evidence for the direct proportionality between force and acceleration. The second law, which is acceleration, the start time of the car was 10.56 and the end time was 11.19, which makes the total time the car traveled less, as it is 1.06 seconds. The velocity is approximately 0.57 meters per second, and the acceleration is 1.05 meters per second square. Newton's third law. The action and reaction forces are equal in magnitude and opposite in direction. If the toy car collides with another car, the force exerted by the first car on the second car is met with an equal force in the opposite direction, results in both cars bouncing back from each other. The magnitudes of both of the forces involved are equal, emphasizing the symmetrical nature of the interaction. Conclusion. In this comprehensive exploration of Newton's laws applied to the motion of a toy car, the experiment yielded insightful observations and confirmed fundamental principles of classical mechanics. For the first law, the toy car, when the car moved at a constant speed, it continued doing so unless acted upon by a net external force, aligning with the law of inertia. For Newton's second law, comparing the motion of the toy car on a flat surface to its behavior on a ramp, the experiment revealed that the incline of the ramp influenced the acceleration of the car. While the angle of the ramp remained constant, the change in acceleration provided insight into the relationship between force and acceleration, reinforcing Newton's second law of F equals ma. Newton's third law. The collision experiment demonstrated that when two toy cars collided, they exerted equal and opposite forces on each other, leading to a symmetrical bounce-back motion. This affirmed Newton's third law, emphasizing the principle of action and reaction. Collectively, these results underscore the universal applicability of Newton's laws of motion in explaining the dynamic behavior of objects. The experiment not only provided empirical evidence for these laws, but also offered a tangible illustration of how they shape the motion of objects in the real world. Through this investigation, we deepen our understanding of the foundational principles that govern the physical interactions and movements observed in everyday scenarios.